Hi, in this video I'm going to explain repeated mesh ANOVA in a bit more detail and how it relates to the general linear model and multiple regression. There were some questions about this. I just want to show you where some of the numbers come from. And this is not something that I find super important to know, because also repeated mesh ANOVA is being used less commonly nowadays. So it's not something I'll really ask about in the exam. How do you get the exact numbers in repeated mesh ANOVA? But it is useful to get an idea of what it looks like and where things come from. Let's jump in JASP. Here we have our example data. We have 100 subjects. We measure them on, let's say, happiness after 3 types of conditions: control, music, book. And there's a between person factor here, which is the animal. They don't change what animal they are over time, but we measure them 3 times in 3 different settings. So that leads to a mixed ANOVA, mixed design. And we can do a repeated mesh ANOVA or mixed design ANOVA. We go to ANOVA button, repeated meshes ANOVA. Specify the within person factor, which is condition. There's 3 levels. So there's a control, music, book. I press tab here to go to the next one. I drag these here and I specify animals as between person or subject factor. Right, and I get my results. I get a condition main effect, condition by animal interaction, and an animal main effect. In this case, everything is significant. Now the weird thing is here that you see there are 2 different tables: within subject effects table and the between subject effect table. So what is happening here? Actually, one way to see it, or the easiest way to see it, is that there are 2 different ANOVAs being run. One for the within subject effects, one for the between subject effects. The between subject effects are the averages of person over time. So the average happiness score, right? That is aggregated over all 3 conditions. So we can't include condition in the between subject effects table. We can only include the effect of animal, because people differ. There might be a different average for cats or for dogs. And within subject effect, we have the effect for anything that varies within person, so condition, but also the condition by animal interaction, because they're still different for each of the 3 measurements. How can we see this as a linear regression model? Let's first go to a different data set. It actually is the same data that we have here. The only difference is that I put these 3 under each other. This we call long data, this we call wide data. In the long data we see, in the wide data we have 1 row for each subject. In the long data we have different rows, or multiple rows for the same subject. So subject 1 is there 3 times. 1 row for the control, 1 row for the music, and 1 row for the book condition. This data has a total of 300 rows, because we have 100 subjects by 3 conditions, so 300 rows. Now we can specify a regression model here, and so far we always saw ANOVA as a regression model. Let's press the regression button, the linear regression. Let's add happiness as dependent variable. And now what do we do? So now I'm going to try to reproduce the within person effect. Actually, I want to show you the interaction effect. Now I get the F value for that. So in the within person effect, we are interested in deviation from the person-wise mean. So when controlling for the average of the subjects for each of the 3 conditions. So maybe some subjects are always happy and some other subjects are never happy. And then we're interested in seeing, okay, given that they're always happy, are they even more happy when we do like a music treatment compared to a control treatment? And we want to control for that there are some individual differences in how happy the subjects are in general. How do we do that? Well, we can add subject as a factor. Subject, we look at our data, our data is here, doesn't look different from condition. It's the same type of variable, just has lots of levels, right? 100 in this case rather than 3. Other than that, same idea. It's a grouping variable, which means we can reproduce it using dummy encoding. We can add it as a factor, which leads to a model with 99 degrees of freedom and 99 model parameters in the regression, excluding the intercept, right? we add 99 parameters and an intercept to model the 100 different person scores over the 3 conditions. Right, so each of these 99 parameters are modeling the differences between the 100 subjects, just like we used 2 dummy variables to model differences between 3 groups. Now what can we do more? We can add animal, but that doesn't do anything. See, nothing changes here. I remove animal or add animal. Oop. Now I added to the wrong one. Add animal here. Nothing changes. That's because our dummy variables for subject are already capturing anything that animal would do. Right? We already have an effect per person. Doesn't matter if they're animals or not, or if what type of animal they are, the grouping is already captured in this. So nothing changes here. I add it anyway, because I want to add an interaction effect. I add condition. Now stuff changes. Yeah. So you have condition as well as predictor. We get dummy variables also. So here we see NA for the animals, they're meaningless, we can't even interpret them. But we get dummy variables also for the 3 conditions, we get 2 dummy variables in our model. Now let's go to model, and I want to add an interaction effect to the model. Between animal and condition, that's actually the one I'm interested in, right? You might want to see, okay, maybe there's a different effect for cats than for dogs, maybe the conditions, the treatments work differently for different animals. And in a real person setting, yeah, you might have some other between person effect you're interested in, right? Maybe age group, for example, you're interested in seeing if a method works for young people or for old people, right? Or maybe men, women, etc. Now let's show you how I got, this is like a table for regression, right? But we're not really interested in this full model. We're interested in the particular effects, the small subjects. So let's show how I got the effect for the interaction effect, which is the easiest to get. Let's add these to the null model and see it as a hierarchical regression model. Now I have in the null model the main effect, the subject variable, which is a main effect, if you will. But you can also just see it as control for the individual means, animal condition, and here I add this interaction effect. Let's add R square and F change. You can see how these 2 models differ from each other with the F test. We get F is 619 with 4 model degrees of freedom on 194 residual degrees of freedom. In our repeated message ANOVA, with this interaction effect, we also got 619 F with 4 model degrees of freedom and 194 residual degrees of freedom. Same thing. Right. So that's how we can see the repeated message ANOVA also as a regression model where we include an effect, in this case interaction, and compare to model without that effect. For the main effect, we can do it as well, but JAS doesn't allow me to specify main effect without interaction effect, so I can't really show it here, but it's the same idea. So that explains this table. That's where that comes from. Now, all right, what about this table? What is this thing? So here we have an effect for animal on 2 parameters for animal, 3 groups, these are 2 parameters, 97 residual degrees of freedom. All right, so we add this plus 1 intercept, but not in the model, we get 100, not 300. So what's this modeling? Actually, this is a separate regression on the person-wise means. So here I just calculated the average for each subject. And I can just do a one-way ANOVA on this average level with animal. You get F is 42.5 with 2 on 97 degrees of freedom. Same thing we got here. That's just it, that's what is reported. So here we're looking at the averages. So the main difference is that we're using a different error variance. For the between person effect, there's no information on the difference between like cats and dogs in the different conditions. They're like the same people in each of these conditions, right? So that's why we have to look at these averages, and that's why the repeat message ANOVA does it like this. Right, so here we have the average per person. All right, so that's just to show briefly how the repeated message ANOVA relate to normal regression models. It's a bit weird because yeah, it's actually two different models. So that can be a bit confusing. And often, actually, people nowadays use this button, linear mix models, which is a bit different, and which I'll explain in the next video.